Hello and welcome to yet another new subject and a new session, and this is on deep learning. So we would specifically be discussing on deep learning for visual computing, and a lot of you might have already heard about this buzzword, and I assume you have heard, and that's the reason why you got interested to enroll out for this course. So deep learning as such has been is sort of what is recognized as one of the major technological realizations which has happened in starting of this whole millennium, and not quite an old as such in terms of when we look into the impact it has created, but definitely it has a very rich history which spans for almost a century, close to a century as of now. So what happened in the last half of a decade was quite interesting. So starting around in 2010 is when this started around, and later on picked up a lot of pitch, and somewhere around in 2014 is when major number of discoveries and major challenges were being solved out using deep learning. So this is one such invention which is not just limited to impacting the software industry and AI driven solutions, so not just purely data and artificial intelligence driven solutions, but they impact us in a large number of ways. So ranging from understanding speech on your phones to understanding what queries you are asking and translating your sentences onto query languages, from there starting on to inferring from images, tagging your photographs, and even autonomous driving of cars by themselves by just looking into camera feeds and views, and even giving down predictive analytics on what is a good time to brake, whether the car ahead of you is now at a mode of braking, and then these systems can even realize stuff before you can do. So these are some of these applications which touch us on our day-to-day lives, and from there it moves on to even a larger and more serious application, and that's in the field of medical imaging and medical image analysis, where you would be using deep neural networks in order to understand and infer about the characteristics of images and even discover newer kind of pathologies and how they are located. So given that this has been a major invention which came down to power a lot of solutions, given that almost for close to 2 decades we have been sitting on a large treasure trove of electronic data, but we did not have enough of compute power, and as well as we did not have enough of a software technology which includes the known mathematics, the optimization solutions, the software implementation frameworks, and the hardware to support all of these together, which could have harnessed the power of this immense amount of data on which we were sitting. And this data is not just limited to say hashtags, they are not just limited to your sales pattern analysis, they are not just limited to geocodes and geotags or coordinates of how your movements is happening, they are also some things which include down much serious nature. So they can be x-rays, there can be surveillance videos, there can be even human behavior analysis videos, then dashboard mounted cameras within cars which can even predict down driving behavior analysis, and if there is something weird or something quite adversarial which is happening on the road while you are driving. So there have been a significant amount of implications which these technology has brought down, and what we are going to do is not just touch down on all of them because it's a large field actually. So this whole aspect of deep learning, this has implications not just in visual computing, it also does impact medical image analysis, it does impact natural language processing, it does impact business and finance, pharmaceutical discoveries, petrochemical industries, autonomous driving, and a lot many more than we can even imagine at this point of time. And by the time we will be finishing off with this course, and as well as say within a year to go, there would be even more significant discoveries and solutions coming down from the space of deep learning impacting all of them. So without keeping all of these too much of a mystery, let's get into what we are going to study. So the particular course which we are going to do is called as deep learning for visual computing, and I would be specifically focusing on the visual aspects of it, and we would be looking into visual data which will include images, they will include videos, They would include other sorts of visual data, including say depth maps from stereo cameras like your Xbox Kinect, which you use for playing your games. They would also be including down medical images as well, and there can be 2D, 3D, 4D, and n dimensional sort of visual data which we can look into. And given that, what I generally pitch forward is that this whole thing is actually a great piece of career advice for ECS graduates or graduates in the field of electrical, electronics and computer sciences. And the major reason I say is something based on the statistics which we know about the market scenario. So how it goes down impacting is something like this. So within another 2 years, or roughly, I'm assuming that most of you would be graduating out by that time, or might have already been in the market. So there, if we look into it, so this whole market is pitched down somewhere around $9.5 billion US, and that does not just include the media, surveillance, automotive and graphics, but again a major chunk of it is related to something which impacts all of us very practically, and that's medical image analysis. Now, given that this is not going to take away the job of doctors, but definitely make down the job of a clinician much more easier, as well as provide down a lot of affordable and accessible healthcare to the billions. That's where we are pitched on to working it out. So on one side of it, if you look into it, almost like 2/3 of the market segment is what is related to media. So this media is in the sense of entertainment industry, videography, gaming industry, and all of them. We have surveillance, which is again a major taker in the field of visual computing itself, whereby you have analyzers running down on all surveillance cameras which are there. You might see them at traffic junctions, at ATM machines when you go down to draw your money, at any of the entrance to institutions, banks, government offices, private offices, anywhere where it's really becoming an essential part of observing people and trying to find out adversaries who might be really hell-bent on making some nuisance over there in their premises. Now, from there, we would be moving on to automotive, which is again a major sector. So within automotives, if you really look into it, then what comes down with automotives is autonomous driving, a major one. Driving assist systems are another one, which whereby the driver is provided down with assistance. So today you have your Google Maps like behaviors, which on your phone it also gives you not just the route prediction, but also gives you the time prediction based on so that's something by making use of data of all the drivers ahead of you who had driven on the same route or on the same road, which helps in getting it. Then they are synchronized along with route maps and way layouts for different traffic densities and how to integrate all of them. And not just that, where we are looking down is today there are certain number of cars which also provide a solution to braking assist. They provide solution on road condition on the driver's dashboard itself, and that's about looking into visually inspecting. And while we as humans can definitely understand a rich treasure trove of data, but then we have a limited bandwidth and capacity to do it, and we might be, while we are focusing on driving the car, we are really cognitively loaded down for just the driving aspect of it, and we are not introspecting on the aspects of the road or the car ahead of us, or maybe the car which is ahead of us. These kind of machine learning algorithms, a lot of them are powered down by deep learning, are what is helping us gain down that and making our roads even safer. From there, it's definitely graphics, which is another major aspect which goes down. Now, given all of this on the medical side of it, what it really impacts is we can look into different kinds of modalities, and they range down from ultrasound to X-rays, and as it goes on. From there to clinical indicators, which include on radiology, cardiology, oncology, and then these are the different clinical verticals which basically get impacted, or the diseases which will be. And the end user for a majority of these are basically hospitals, diagnostic centers, and secondary research centers, which may include even pharmaceutical labs. Now, given that we have been able to, and we are striving on to make real big impacts onto this field, and deep learning is definitely powering a lot of what we are doing today. Where we are looking down in the future is something of this sort. So visual computing would definitely be one of the major impact makers in the field of medicine itself, and this is from one of our earlier articles which we had published on the future of operating rooms. And this is what a future of operating room looks like, though this is from a real one which is already on a prototype test scale, realized down for showing it out to the world how a futuristic operating room would look like, where you would have not just surgeons operating down on a patient, but you would have a lot of machines which will be assisting them, and a major of these machines are all compute oriented, which will be making use of this real time data of the operation going on, pre-operative data in the form of CT and MR scans of the whole patient over there, their projective anatomies which you can see on this transparent screen over here, and these are assistants which it would provide down. So as in, like, you can get your road driving assistance on your cars, in the future these systems would be helping surgeons, provide them assistance on how to drive down a particular tool and a particular surgery. So at the end of the day, this is the golden dream which all of us have in trying to get down even much better quality of life and a quality of health also. Nobody wants to become sick in any way, but in case you fall sick, in case there are accidents, can we really ensure that there is a better treatment? And a lot of it, because this is a practice which is heavily vision guided, which means that humans look into it with our eyes, we see, surgeons inspect visually, and accordingly they take a decision and keep on operating. So the whole objective is, can we combine all of this, integrate that, all the learning aspects of human into machines as well, so that these machines can actually help in solving smaller pieces and blocks of the whole bigger task to be achieved. And down the line, as we are able to achieve all of these solutions, what we would be seeing is a whole ecosystem and a product being built around that. Now, given that, let's get into what we would be learning now. So typically this course is organized as a 12-week course, and each week itself has its own takeaways. So we will start with the first week, and that's what we are doing now. So today I am introducing you to the course overview and what this whole aspect of visual computing is, and subsequently we will be learning about visual computing aspects from the classical way of extracting features. And the reason I would be covering that in one of the lectures is so that you understand what is the relationship between these classical aspects to why are we moving on to the deep learning aspect of it, and where do we gain an edge in terms of moving from a classical aspect to a deep learning aspect. And subsequent to that, I will be introducing very simple neural networks, and we would be having down lab sessions in between as well, where we would be making you go through not just a walkthrough, but how to set up your own systems and machines on your end, and how to even set up the HPC resources so that you can get access to a much higher compute power on your side, which might not typically be available on your desktops and laptops itself. So from there we move on to week 2, where we would be starting with multi-layer perceptron, which is the basic model for any kind of a neural network, and then eventually enter into deep neural networks. And over here we would also be, so as we go down on each of these weeks, while we will finish off some part of the theory, we would also be having a matched out lab session. All the lab resources, codes and data and everything, how to pack down data, these instructions will be released on a separate GitHub link which will be provided to you, so you can make use of. So as and when we come down to the lectures going down through the code walkthrough and programming implementations, we will be getting down into more of details of how to access out. And we expect that these GitHub links are going to remain permanent. That's what we have been doing for our earlier courses as well, and so that you can get back at any point of time and relook into that. So on week 3, I would be starting down with the classical representation of a deep neural network, and called as an autoencoder, which is an unsupervised learning mechanism and used for doing something called as a representation learning. And here we would be relooking back into what we do in this week's lecture with classical methods of vision using textures, and try to draw an analogy between these different kind of textures to what we learned on with a simple autoencoder in the form of representations. So from there, going down to week 4, we would be doing stacked sparse denoising autoencoders, and a particular concept called as ladder training, which really helps in training these networks much faster and without much of an issue as we would experience with other kind of a deep neural networks. So from there we move on to week 5, and in week 5 we would be looking into cost functions, learning rate dynamics and optimizations, and this is where how this whole learning happens. So typically when we say that something has to learn, so there has to be certain aspects over there, what is meant by learning and how does something learn. So these are the concepts which we would be covering down in week 5. From there, going on to week 6, we will start with the biggest celebrity of the lot, and that's called as a convolutional neural network, which has been pitched today as one of the major inventions of this particular century, if not the millennium at the least. So we start with the basic building blocks of a convolutional neural network, including explaining you why is it called as a convolutional one, and then where does the neural network come from. So finishing off with week 6, when we enter week 7, we would be doing some of the very classical architectures of convolutional autoencoders, and then enter into deep convolutional neural networks, and get down with the examples of AlexNet and VGGNet. So when we will be doing down these examples on AlexNet and VGGNet, so these are basically on different people or different groups who were their inventors. So we would be going down in a surgical fashion onto basically dissect out the different aspects of the network, what are the building blocks over there, while these networks are being built, what will be the computational complexity achieved, what will be the data complexity over there, what will be the model complexity. So this basically means that how much time, how many number of CPU seconds, or say number of time clock cycles you would be needing in order to execute these networks per image. What will be the size of the image this can deal with, what will be the dependency between the image size or the input to the output size over there, as well as what will be the dependency in terms of the model weight, which is you are going to store all of this network, everything together into one sort of a file. So what will be the size of the file, and the interesting part is that you can actually calculate these on pen and paper, and that's what we would be doing in week 7 starting over there. Next we enter down week 8, and that's where we would go down to the recent advancements, and these include down GoogleNet to ResNet to DenseNet, and these are some of the very deep networks which have been there. So these are the ones which have been proposed in the last 3 years itself, and these are the winners of one of the major challenges called as ImageNet challenge, which we would subsequently come down. So we would be surgically understanding each of them, go down to their implementations and code level walkthroughs, and how to reuse them if you would like to. From there we get down into week 9 into understanding computational complexity, and this is where we revisit what we do in the earlier 2 weeks in terms of understanding how much of time it would require, but here into much more of a details, and also try to get down into much deeper understanding of can we reduce the time in certain way, and what can be the aspects of not to compromise on the quality but yet get a reduced time implementation over there. So from there we would enter into another important aspect called as transfer learning, and the whole aspect of transfer learning is that can I have a network which has been pre-trained or which has been basically trained and in order to do a certain kind of a task, and can I use it to do another kind of a task. So if there is a network which has been trained to segregate bananas from oranges, now can I use it to segregate say a thief from a normal person. So this is a typical example of what I would put down as a transfer learning problem. So not just these, but even more complicated ones, and how can we use them. So we'll get down into domain adaptation and transfer learning over there in week 9. From there in week 10 we so while all of these have been on classification problems, in week 10 we would enter down into something called as localization issues. So if can I localize down certain objects in the particular image. So an image might have say a lot of fruits over there and a dog standing in the middle of it, and if I just want to localize the dog but not all the fruits, then can I do it. The next part is semantic segmentation, and this is about pixel to pixel wise labeling. So can each pixel over there be labeled down in a given image using a deep neural network. So we will be going down through this important investigation as well, and also walk down on the implementations. Week 11 we would be starting down with another interesting discovery which has been coming down in the last few years, and that's on generative models, and this is about can we use these kind of deep networks in order to generate images. So if I write down a word, say an apple with a black patch, can it actually generate an image of an apple with a black patch on it for me? And so we'll come down to this really interesting aspect of generative modeling and then using adversarial learning in order to do that. And From there on to week 12, we entered down on sequence modeling with recurrent neural networks. And for us, in terms of visual computing problems, the sequences are all video frames over there. So all frames of a video, if you place it down, so they're basically images which acquire in a particular time generated sequence, and that's what we would be trying to do with recurrent neural networks. Now, given that this is the organization on how this whole course is organized, if we look a bit into the history, then visual computing as such is not something new, and it has a history which is quite rich and more than 35 years. So I do take down this interesting paper on medical image analysis though, and then this is from the journal from the IEEE Transactions on Pattern Analysis. And the reason I was doing down is because this is one of the most comprehensive, and while it does draw down correlates with medical image analysis, but nonetheless the visual computing is also almost of the same sort of a running behavior which has been there. So around in 1980s is when the whole thing started down, and a major reason for it starting down was that digitization of images was now possible. So people had line scanners invented by then, and then you could be scanning down images, and there was enough of a compute power now with reprogrammable silicon based computers in order to do it, and you could bring it down onto consumer grade applications. And from there it started down with knowledge based approaches in the late of 1980s to early 1990s, and from there from 92 to 98 is when 3D image analysis was becoming a bigger craze. So can we analyze out volume? So people were no more happy with pixels, but everybody was looking at voxels, and bigger data, more amount of data, more complicated calculations, and more space requirements. So can we really go beyond that bridge? And once that was done, so starting in the early of this millennium, the major thing which happened was shallow reasoning was making a bigger way. So we were getting down machine learning based solutions into our consumer grade products. So you had cameras which could be detecting down faces, you had cameras which would be shuttering down only if the face was smiling. Now you had gaming consoles which had cameras which could track down your face and your hand movements over there and help you to interactively play video games. So these were some of these small things which were happening. There were interesting aspects in the field of medicine like CAD systems which were helping find out benign masses and segregate them from malignant masses on X-ray images. And not just that, there were vessel segmentation algorithms which started coming down, and there were major aspects which were good. But all of these, what was happening down was still with a limited compute power, and the amount of reasoning was what is called as shallow reasoning. It wasn't something which is called as a complex reasoning as we say, and that's something which started growing since 2010 and beyond it. And what this complex reasoning basically meant is that say I give the camera, I just have an image given down to the computer. Can it describe a semantic equivalent of the scene, or can it tell me what should I do next that given this is the frame? So today's cars, if you look at it, so there are ADAS systems, driver assist systems, which actually provide you an input on what should you be doing. If you look into your Google Maps, you would see another interesting fact that if you are somewhere at a crossroads and you have two different ways to take, and both of them will be leading to the same sort of a destination, but then one of is experiencing a heavy traffic, whereas the other one is where you won't be experiencing a lot of traffic jams and lags behind over there, then it does give you a prediction that this route B is 10 minutes shorter than route A. And all of this is where comes down the complex reasoning. So earlier it was just computing. In a shallow reasoning, it was just computing down what is the travel time estimated to be taken down. In complex reasoning, it's actually telling you what you should possibly be doing. So these are two different aspects which come down from shallow to complex reasoning. While shallow reasoning will deal with only one simple aspect of the problem, which is not so complicated even for humans to tackle down. Whereas for complex reasoning, it would be giving down an inference and a solution which is much more human like and what you would be expecting down from a machine to come down. So given all of that, as we enter into 2018 and in this early part of it, where we see major challenges in visual computing is one of them is activity classification within videos. So what are the different actions being taken down within videos? There are aspects of computational cameras and displays. There is computer vision in sports, and you might have been watching. So as Indians, we are quite crazy behind cricket. So you would be looking down into cricket matches, or even now that recently we just finished up the FIFA under 18 football tournament going down. So over there, in case of sports, you would be seeing down there are a lot of computer vision applications, and these are not just limited to tracking down crowds or anything, but there are individual player trackings which goes on, and this analytics is quite critical for sports analysts and even for budding sportsmen who need to understand player strategies and team playing strategies over there. So computer vision does play a significant aspect over there. From there it goes down another quite rising topic of today, which is called as visual question answering. So today, if you give an image to a computer and then keep on asking questions, it can keep on giving you answers in a human like way. So if I just say this is a typical system of where you have a VQA or visual question answering given down. So this is an image given down to the computer, and what it asks is what's the mustache made of. So from there, what it says out is that bananas. Now this computer does understand where is the location of face and the location of a mustache with respect to a face and what should it be looking like, and then it identifies what is the actual object which that's made of, and then says out banana. So this is a visual question answering or something you would be doing with a toddler yourself. So from there goes down these aspects to autonomous driving, which are a real major impact creators as of today, with major investments going down. Now, given that we do understand the aspect of visual computing as of today, now what I have is some sort of a career advice for most of the aspirants over here. So one is do definitely find out a research challenge over here. So one way is grand challenges in biomedical image analysis is my personal favorite, where we put down at least on the field of medical image analysis, we do love sharing our data and putting down challenges out over there, problem statements, and what we really seek to solve along with clinical collaborators. The other place where you can really get down is on Kaggle, and in Kaggle you will be getting down a lot of these vision related challenges coming up recently. So the other place to read down and find down what are the recent ones are CVPR, which is the International Conference on Computer Vision and Pattern Recognition, which is jointly organized by IIIT Computer Society and the Computer Vision Foundation. From there, ICCV, which is the International Conference on Computer Vision, the European Conference on Computer Vision, the British Mission Vision Conference, and the American and the Asian Conference on Computer Vision. So these together are the major places where you can see down not just on vision, but a significant amount of contributions coming down in the field of deep learning and its applications as well. So given all of this, I would be getting down onto what are the toolboxes which you can be using over here. So in order to achieve what we are going to solve, the major toolbox which we need is Anaconda Python. So this is Python 2.7 based, which we will be using down through our lecture. So we are not using Python 3 in any ways, everything is 2.7 based. Then for our deep learning aspects, we would be using PyTorch, which is a library compatible on Python and has accelerations available for deep learning applications itself. From there, MATLAB is another interesting one which you can do for some tidbit experiments and initial part of learning, but we might not be using it together for most of it. And CUDA is used for accelerating your learning experiences with an NVIDIA GPU. So having given all of this, where to read for machine learning and deep learning specifically, you can go down through these journals which include pattern recognition, pattern analysis and machine intelligence transactions, then the journal on machine learning, journal of machine learning research, and nonetheless. So not just journals, but there are important aspects of looking down into conferences as well. So CVPR is one of the major ones. For machine learning, do definitely try to go through ICML, ECML, SEML, and NIPS. And for computer vision, you can go down through ICCV, ECCV, and ACCV, which I had underlined in the previous ones. So for listening and socializing more, it's better to start going down to workshops and schools, winter schools and summer schools. So International Computer Vision Summer School is one of those ones. Then the machine learning summer school, the deep learning summer school are some of these interesting ones which happen. Now on the Indian context, it's definitely worthwhile to go down to conferences which include ICVGIP and the NCVPRIPG. Now these are just the crux of what we have to do and some pointers to where we go down. As we go through the rest of the lectures over here for this particular series, I would be putting down pointers on interesting aspects, on interesting places to look down through your notes, and then the book chapters which you would be doing. So with that, stay tuned and geared up for the next lectures, and as we come, and keep on enjoying this. Thank you.